Hi, welcome to this lesson on linked lists. At the end of this lesson, you should be able to list the properties of the linked list data structure and write a C++ program that implements the linked list data structure. So what are the properties of a linked list? A linked list is a linear data structure in which the elements are not stored at contiguous memory locations, as opposed to in arrays where they are. The elements of the linked list are linked together using pointers. Have a look at this diagram, which indicates the basic structure of a linked list. Each element is represented using a node, linked together using these arrows that represent pointers. There is a special pointer to a node called head, which allows us to access our linked list data structure. Let's implement this linked list using C++ code. We can begin by including some basic libraries to help us write our code. Let's also import the C standard library so we can make use of the built-in constant null. Before we begin, we first need to define our nodes. Let's create a class definition to do this. Our nodes will be able to store an element and a pointer to a type node. Now that we have our definition for our nodes, let's begin building our linked list data structure. We will create a separate class template for linked lists objects. We will call this linked list, and it'll have the following public methods. First, a constructor, a destructor, a function that is able to return true if our linked list is empty and false otherwise. We will call this function isEmpty. We can also use the constant keyword to indicate that this function will not change any objects from this class. Next, we can have a function that returns what's at the front of our linked list. Let's have it return a constant reference to a string, since our nodes require string elements. Our front function also won't modify any objects from this class, so we can indicate that using the const keyword. We need a way to add nodes to our linked list and remove nodes from our linked list. Let's add 4 function definitions to our linked list class to be able to manipulate our linked list data structure. So let's start by creating a function that is able to add a node to the linked list. We will take a constant reference to a string object as an input argument. Let's call this E. Next, we need a way to remove the front element. We can have a function definition to add to the back of our linked list. It'll also take a constant reference to a string object and have a way to remove the back of our linked list. it would be nice if we had a way to dereference objects from our linked list class and have them be printed nicely on the screen for us to see exactly the contents of our linked list. So having something like cout with the out operator dereferencing an object from the linked list class, and from this we could have something like this. Ritesh Ajoodha. These are elements from my linked list: cat, dog, monkey. Then the last one pointing to a null. This would be great. So let's overload this operator so that we can print out our linked list in a very nice way like this. We can do this by creating a function called operator which overloads this operator. Let's do that. We will create a friend function which returns an OStream, a reference to an OStream object. The name of our function will be operator, and we will take in two arguments. One, the OStream object, which we will pass by reference, call out, and a constant reference to a linked list object. Which we can call object. We will implement these functions in a minute, but we have to first define them, and we do this in this way. Right, finally, we can set our private members of this class, and the only private member of this class, going back to the diagram I showed you at the beginning, was head. So let's define head as a private member of this class. We can do this very easily by defining a pointer to a type node called head, and we're done. Now that we have our linked list class definition completed, we now have to implement each of these functions listed from line 15 to line 22. We can do this outside the class by using the scope resolution operator. To use the scope resolution operator, we simply indicate the name of the class, the function which resides in the class, and code blocks where our implementation of the function will go. I will now skip ahead and provide the implementation space for each of these functions. As you can see, I now have each of the implementation spaces for each function. Here is the one for the constructor, here's the one for isEmpty, for the destructor, to check the front element, to add to the front, to remove from the front, to add to the back, and to remove from the back. Let's now begin implementing these. Let's begin with the constructor. The only member that I do need to initialize is head. So let's initialize head as a pointer to a node, which will be set to null when an object from the linked list class is initialized. If we want to check if our linked list object is empty, if we know it was initialized with head set to null, all we would need to check is if head is null. We can do that by saying return true if head is null. With regard to our destructor, what we would need to do is deallocate each of the new nodes allocated in heap memory using new. We can do this using a while loop and removing from the front or from the back each node which was added into this linked list. While the list is not empty, remove front. In this function, we wanted to return the element of the front node. We can do this by simply returning a dereferenced head. adding to the front of our linked list is a 4-step process. We first need to initialize our new node, set the element's contents to new node, set new node's pointer to point to the head, and finally update the new head as new node. Removing the front of our linked list has a similar process. First, we set a temporary variable pointing to the head of our linked list. We can call this old head. Then we can move our head pointer to the second element of the linked list. We say head is equal to heads, next. And finally, we can delete our old head using the delete keyword. Adding to the back of our linked list is similar to adding to the front of our linked list, except since we can only access our linked list using the head pointer, we would need to iterate through our linked list to get to the end of our linked list so that we can append a new node to its back. Let's do this. The first thing we'll do is declare a temp variable. We will call this temp and set it to be initialized pointing to the same thing the head is pointing to, which is the first node. The next thing we'll do is initialize our new element, our new node that we will append to the end of this linked list. Let's call it new node for consistency. We now have to set our new node's element, which is passed as an argument to this function. Now let's consider two cases. Firstly, we could be adding a new element to our linked list spec which already has elements in it. If we're doing this, then we need to check if our head is equal to null. If our head is equal to null, this will be the new element, the first element and the last element in our linked list. If our head is not null, then we would have to iterate through the linked list to find the last node so that we can append our new node next to that. So let's firstly check if head is equal to null. If it is, it'll tell us that our list was empty. If it is, then all we need to do is set our head to be equal to our new node, and we're done. If it's not, we would need to iterate through our linked list until our temps next is equal to null. And when we get to the last position, we would need to set our temps next to be equal to the new node, which then adds to the back of our linked list. Removing from the back of our linked list is also simple. We create a temporary variable, but this time we don't want to move our temp to the last node, we want to move it to the second last node so that we can rearrange the pointers of the last two elements. So all we would need to do is find the second last position, which is where temps next is not equal to null. oops, temp is equal to temp. Next. Thereafter, setting the last node, since we have the second last position, let's create another temporary variable called last node and make that equal to temp's next node. And now that we have the second last position in temp and the last position in last node, we can simply delete the last node and make temp's next null. Try to draw a picture of what's happening in this function using the linked list structure that I showed you at the beginning of this lesson. The last thing that we need to do in our linked list class is define this operator overloader, which is a friend of this class. Since this is a friend of this class, the operator overloader function can access our private members of the linked list class. Let's implement this operator overloader. Well, our return argument will be an OStream object. The name of the function will be operator. We're overloading this operator. The first input argument, as we wrote it down here, we could just cut and paste this. Let's do that. So we have the OStream object as a return, the name of the operator overloader, the operator which we're overloading, an input argument, which is an object from the OStream library, and also a constant reference to an object created using the linked list class. Let's now implement this function. The first thing we'll need to do is, the objective here is to print out our linked list using a while loop. That's what we're doing in this operator overloader. And the purpose of having this is so that we could, when we output an object from the linked list class, for example, my list, it should appear in a very nice concatenated string onto the terminal. So let's implement this. Well, the first thing we need to do is create a temporary variable which will allow us to iterate through our linked list. The linked list passed to this operator overloader is contained in this object specification. So we can just say object.head, and this will give us the head of this linked list object. This is allowed since the operator overloader function is a friend of the linked list class. So now it can access its private members. Great. Now we can simply increment through our linked list object, printing out the elements as temp iterates through it. Oops. Finally, we can output the null character. This is a representation of the null at the end of the linked list. The last element, remember, the last element points to null, and we can return out, which is the OStream object which we received in the beginning. Great. Now we are ready to test our linked list data structure, and we can do this using the main function. Let's begin by initializing our linked list data structure. So linked list we create a pointer to a linked list object called myList, and this is equal to a new linked list, specifying the constructor. Well, if we see out our linked list, let's see what we get. Well, what we would expect to get is, since myList is an empty linked list, outputting myList using the operator overloader should skip the while loop and move straight to out. Let's see what happens. I didn't save it. Let's save it quickly. MyList.cp. No, it's not called MyList, it's called linked list. Oh no, many errors. Okay, let's have a look at what the error, of where the error might be. So it says linked list on line 13. Let's go up to line 13. We see that the class definition for linked list may not be defined. So this is an incorrect definition. It appears that we forgot our semicolon at the end of the class linked list. So let's add it in. Alright, we save it. Let's try to run it again. Oh, also I've just noticed that the passing by argument is incorrect. Const string, your ampersand goes right after string. Let's try it again. Another error on line 29. On line 29, we see that our node star head has already been defined, but on line 29 we've defined it again. So we can simply remove our definition of node head again and save our program, run our program, and now all of the errors are gone. So when you have errors, don't panic. Just read the error, go to the line where the error, where the compiler indicates there might be an error, and attempt to debug it. Nobody's code is perfect. Right, so let's now run our program. Great, let's have some fun. Let's add new elements to our linked list and see how it copes with our implemented functions. Let's begin with adding to the front. So let's say myList add front Beethoven. Let's add Schubert. Oops. And now let's print out our linked list. Let's see what happens. See, Schubert, Beethoven was added to the front, then Schubert was added to the front. Let me just make this a bit smaller. I just moved some windows around so we can see more clearly what's going on here. So we will compile our linked list class and we'll see that Schubert and Beethoven have been added to our linked list. Let's now remove from the front of our linked list. So myList remove front, okay, and then let's print out our linked list after we remove from the front. As we expect, Schubert is removed from the front of the linked list. Okay, great. Let's now add to the back of the linked list. myList add back Puccini. And let's print out our linked list after we've added to the back of it. Let's see what happens. Okay, so Puccini is now added to the back. And finally, let's remove from the back. So we've used all of our functions. The last one is my list. Remove back, and let's print out the linked list to see what happens. And as we expect, we remove Puccini. Right, that's how we implement a linked list.